we're talking about was done in close collaboration with a few people, namely Nikita Strahansev from the University of Zurich, Konstantin Tikhonov from Skolkovo Institute of Science and Technology, Mikhail Katznelson from Radboud University, and Andrei Bagrov from Uppsala University. So,
Tom, I'm sorry, your audio is really a bit strange. Do you have a mic you can use maybe, or it's really?
Is that better?
Yeah, that's much better. Yeah, thank you. Yeah, there was some distortion. Yeah. Okay, great. Thanks.
Sorry about that. Science structure has been mentioned a few times during this conference already. For example, that the NQS NZ works better when the science structure is known in advance and one doesn't have to learn it. Or that in the case of frustrated magnets, it might be the limiting factor when training the NQS. And I'd like to make this statement explicit and claim that the science structure is the reason why it's so difficult to tackle frustrated magnets, and specifically that it's the generalization of the science structure that's the main obstacle. To illustrate this claim, we'll consider three models shown in the slide, namely the J1, J2 model on the square lattice, an isotropic triangular lattice, and an isotropic Kagama lattice. And the ratio J2 to J1 allows us to vary frustration and maybe even turn it completely if we set the ratio to 0. Okay, I think it's really important to recap the definition of two concepts, namely expressibility and generalization. So expressibility is the ability of a neural network to accurately represent the data. So this is what people have in mind when they say that some neural network architecture is actually a universal approximator. But there is a thing called overfitting, which is shown on the picture here. Namely, we can make our ansatz really expressive, but then if we add more data, it will get it completely wrong. So that's where generalization comes in. And generalization is the ability of a neural network to correctly predict results in samples which were never encountered during training. So the next question is, how does one study generalization? And for that, our goal is to set up an isolated experiment where the effects of generalization can be clearly seen. We'll focus on supervised learning, and we'll be using ground states obtained by exact diagonalization as target states. For system sizes for which exact diagonalization is feasible, we can actually store all the coefficients of the wave function and sample from it exactly. In that way, there's no Monte Carlo and no probability issues. Also, sampling effectively splits our Hilbert space basis into two parts, one which we've seen during sampling and the other which we haven't. And we'll use the first part for training, and it's usually quite small, on the order of 1% or maybe 1/10 of a percent. And we'll use the remaining part as a test data set on which to benchmark our networks. Okay, so now to training. So our Hamiltonian is purely real, so the ground state is real as well. And what we do here is, instead of splitting the wave function into amplitudes and phases, we split it into amplitudes and signs. And then we employ two different neural networks to separately predict the logs of amplitudes and signs. Thus, we have a regression task and a binary classification task. Then intuitively, one would say that binary classification is simpler than regression. So let's start with that. So what I show here is results of training different architectures on a tiny subset of the Hilbert space basis. So we compute the overlap with the exact ground state and use it as a metric. Note that this overlap is computed on 99% of the Hilbert space, which was never seen during training. And interestingly, in the unfrustrated phases, which are marked white, unshaded on the plots, neural networks perform quite well and can learn the science structure. However, they do struggle in the frustrated cases. And the second thing to note is that different architectures can have completely different generalization. So here we considered 3 different architectures, namely 1-layer and 2-layer dense networks, and a convolutional neural network which respects translational invariance. And one can clearly see that the CNN performs much better, which is most likely due to the translational invariance. So let us now add the regression to the picture. So we can employ like hybrid states in the sense that let the neural network predict amplitudes and we'll take the signs from the exact diagonalization or the other way around. Then if we still use overlap for both cases as a metric, we can actually compare how difficult the tasks are. And yes, one can see that in the frustrated case, the generalization quality of the amplitudes drops considerably, but it's still much, much, much better than that of science. And the data here is shown for 24-site Kagame lattice, where the situation is rather extreme. And so the conclusion is that science structure is actually much harder to learn, even though it's a classification task. But can we do something about this problem? So of course, one can try to tune the hyperparameters, add some more symmetries, or play around with neural network architectures. But another natural question is, what if we just feed more data to the neural network? So we've done exactly that. And here on the x-axis, we have epsilon train, which is a fraction of the Hilbert space basis which was used for training. And intuitively, one would expect that the generalization would grow gradually, but this is not the case. It looks like it almost exhibits a phase transition at some critical training data set size. So it looks like there's a minimal amount of data that is necessary to say something meaningful about the science structure. And this brings me to the most optimistic slide of the presentation, I think. Oh no, by the way. Also notice the difference here for 2 systems. That's in the case of Kagame lattice. If we go to the frustrated case, for example, J2 or J1 equals 1, then we need much more data to learn the science structure, where in the square lattice, this difference is not so pronounced. So yeah, back to the most optimistic slide. Namely, how does the critical training dataset size scale with the system size? So 2 things here. We use n critical instead of epsilon, because as we go to bigger systems, fraction of the Hilbert space becomes a somewhat strange measure. So instead we show absolute number of samples. And we use square lattice here since it's a bit easier to diagonalize. And the nice thing is that data set size grows really slowly. For example, we've added 12 spins to the system, and the critical data set size only grew by a factor of 10. So there's some hope for actually solving the problem. Now let me address two typical concerns or questions raised about experiments in this work. First of all, it's been suggested that we simply don't have expressive enough networks, and that's why we can't learn the sign structure. So let me assure you that this is not the case, and even the simplest neural networks can express the state really well, as can be seen at the top panel. Expressibility is shown in black dashed lines, and indeed it drops down for the Kaggle lattice a bit, but it's mostly due to us being lazy and not training for a long enough period of time. And the second concern is that we've done supervised learning. And when you search for the ground state, you're typically using VMC, which is a completely different technique. So how do our results relate to, for example, stochastic reconfiguration? So for example, for the stochastic wave function optimization, the method that's been mentioned here before, it's really trivial because at each step of the optimization, you're actually doing supervised learning. But in the case of VMC, it's not that trivial. So we've run some experiments, and at the bottom panel, you can see the results of stochastic reconfiguration simulations, and they clearly resemble the behavior of generalization quality really well. But if you think about it more carefully, this actually should be the case, because what you typically do during VMC simulation is you sample some spin configurations, then compute, for example, gradients or other quantities, and try to update your variational parameters based on that. Even if you repeat this procedure like 100 or 1,000 times, for a big enough system, you've still only seen a tiny, tiny fraction of the Hilbert space. Then later on, we want to compute correlation functions, for example, or other observables, and we still hope to get some reasonable results. And this is the very definition of good generalization. So let's recap what we've done so far. So we started by considering sign structure generalization, and we saw that it mimics basically that you can trace back the different phases in there, and that generalization is much worse in the frustrated phases. Then we saw that it's indeed the task of learning the signs rather than amplitudes that's so difficult. And finally, we saw something interesting, that there is some critical amount of data that you need to feed your neural network to get some decent generalization. And for a bit more thorough review of the topic, check out our paper. And I'd like to thank you for your attention.